Hello friends, for the TYBSc Physics, the paper Mathematical Methods of Physics of Savitribai Phule, Pune University, Pune. Let's discuss few multiple choice questions on chapter number 4, that is spatial functions. Please note, here in this chapter, most of the questions are memory based. You have to remember these three spatial functions here, basically legendary polynomial or legendary function, Harmonic function and Basal function of the first kind. Now in theory we have learned earlier how to arrive at these three different types of polynomials or the functions. So first we have to solve these three differential equations, that is legendary, Harmonic and Basal differential equations, using the method of separation, Frobenius series solution method. Once we get that solution, using certain boundary conditions, we can get polynomials. So this is one way. Second way we have learned is that we can use certain generating functions. Third way we can go, that is for using the Rodriguez formula. Also for every such type of function there exists such Rodriguez formula, and as well for each and every spatial function there exists certain important properties. Out of that properties, the parity of this function or the type of this function, as well as sometimes we go for the three terms recurrence relation for each of these functions. So these are the few important things over which we have to concentrate while solving certain multiple choice questions over this chapter, that is number 4, or the spatial functions. So let's see here. Now we'll also see some of the questions, 15-16 total questions we are going to discuss here. First question is, the generating function for the legendary polynomial is. Now there are 4 options given. A is g of xt is equal to e raised to twice xt minus t square. B, g of xt is equal to e raised to x upon 2 into t minus 1 upon t. And C is, option C is g of xt is equal to 1 minus twice, actually it is not t into, not into t, but it is xt. So this, there is some correction. This is simply x into t. So let me take the pen. So here it is, this is to be xt, so twice xt plus t square raised to minus half, and none of this. So out of this we have already seen in theory this function g of xt, if it is expanded around t is equal to 0, we get a series for n equal to 0 to infinity, and this is expanded in such a manner we get certain functions which are called as p(n) of x into, this is t raised to n. So this is the, we get a power series in t raised to n with certain coefficients, and these coefficients are nothing but the legendary polynomials. So here the correct generating function for this we have to remember is this C, that is g of xt is equal to 1 minus twice xt plus t square, that raised to minus half. Now making that particular arrangement, so making this to be taking t to be common of both of these two terms, etc., one can expand, this is 1 minus x raised to minus half. So using that expansion we go for this type of power series in t raised to n, and coefficient for every power of t raised to n, that gives you all legendary polynomials p0x, p1x, p2x, etc., etc. Now question 2, the generating function for Harmonic polynomial is. Now here also the generating function for Harmonic polynomial, here this is again a memory based question. Earlier we have seen this is the generating function for the this g of xt is equal to e raised to twice xt minus t square. This is option A. B is equal to g of xt into is equal to e raised to x upon 2 into t minus 1 upon t. C, option C is g of xt is equal to 1 minus twice, again this is x into t plus t square raised to minus half. We have seen this is already a generating function of legendary polynomial. So options, the correct option in this case is as given by this 1 upon twice xt. So this is the correct option for this Harmonic polynomial, as we know here it is given by e raised to twice xt minus t square. So remember, this is the correct answer for this question number 2. That is option is correct, option is A. Now let me revise these things. So this is question 2, option is A. Now question 3, the generating function for the Basal polynomial of first kind. So here already we have seen this is for the polynomial. What we have seen just now is a Harmonic. Then this is the generating function for Legendre we have seen, and what remains here is none of this. This is not a correct option here. So this g of xt is equal to e raised to x upon 2 into the bracket 1 minus 1 upon t. This is the generating function for this Basal function of the first kind. Okay, so Basal function of first kind. This is the generating function as we know. So in all of these cases, this generating function is to be expanded around t is equal to 0. So we get an infinite series in power series in terms of t raised to n, and whatever coefficient for every t raised to n, these are respectively called as Harmonic polynomials, Basal polynomial of first kind, as well as Legendre polynomial of different degrees or orders, and that is how these generating functions are to be expanded. So this is what a comparative questions 1, 2, 3 that gives us an idea regarding the different types of generating function. Question number 4, this is a property Pn of minus x is equal to minus 1 raised to n Pn of x, and Pn of minus 1 is equal to minus 1 raised to n are the properties of, as we have already seen, that this all Legendre polynomial, this is a convention, Legendre polynomials are defined by this symbol Pn of x, where this n is an order, and this is what, therefore the property mentioned here is the property of the Legendre polynomial, and this is what the property already we have discussed. Replacing this x by minus x, what happens to this sign of that function Pn of x? So this parity operator, if it is operated over this, it either changes a sign positive or negative of the given function. So Pn of x. So replacing this, that means parity operator is operated over this x, we are replacing x by minus x. So see the change of the sign of that function, whether it remains same or it changes. If it remains same, we call it to be a positive parity, and if it is doesn't change, or if it changes, when the function of that sign of that function remains same or remains positive, or there is no change of the sign, then we call that to be a positive parity. And when there is a change in the sign of the function while this parity operator is operated, we call it to be an odd function or odd parity, and therefore these properties are basically properties of the Legendre polynomial. Then question number 5, Pn of 0 is equal to minus 1 raised to half. Okay, in our textbook earlier we are using this Pn here, okay, not there. So Pn of 0 is equal to minus 1 raised to n by 2 and multiplied by 1 into 3 into 5 into 7 dot up to n minus 1 upon 2 raised to n into n by 2 factorial 4. Now this is another area, a very important property of this Legendre polynomial. And how to obtain this property? Here what we have to go is, for that we have to decide we have to go for its generating function g of xt. We are asked Pn of 0, that means we have to put this x is equal to 0. So this is g of 0t. Now this g of 0t is, if its function is x is minus twice xt plus t square, so put x is equal to 0. So we will get this to be 1 minus t square, that actually it is raised to minus half. So this is raised to minus half. Then use this expansion 1 minus t square raised to minus half. So use this expansion 1 minus x raised to minus half. Use this expansion. Using this expansion we get this particular term here. Nth term is given to be minus 1 raised to n by 2 and 1 into 3 into 5 into 7 like this, divided by 2 raised to n by 2 and multiplied by n by 2 factorial. And you will find that when we go for this entire things, it is observed to be Pn of 0. So when this particular series is expanded, all odd terms disappear. odd terms do not appear in this expression of this t 1 minus t square raised to minus half, and that's why all odd terms, that means when n is equal to odd, all Pn of 0 or P odd n of 0 is equal to 0, and for this n is equal to for n is if n is replaced by n by 2, then we get this series here. This Pn of 0 is equal to minus 1 raised to n by 2, and then 1 into 3 into 5 into 7 etc. up to n minus 1 divide by this is 2 raised to n by 2 and n by 2 factorial, and this is for odd n by 2. That means when n is replaced by, that means when n is odd, then we get Pn of n is equal to 0. If n is even, then Pn of 0 is not equal to 0. It is Pn of 0 is equal to minus 1 raised to n, then multiplied by 1 into 3 into 5 into 7 etc. So for even n, that comes to be p to n. Okay, so this comes to be p to n, and when this n is replaced by n by 2, then we get this particular series here. So here, if therefore correct option of this question number 5 is neither this odd nor even nor positive nor negative. So here this will be obtained by when this n is even, and when this n is replaced by n by 2, then I'll get this is the outcome of this particular expression. Otherwise, if n is even, so replace this n everywhere by n by 2 by n, whatever we get here is that is called as the expression for that. So this is what one property of this legendary polynomial that can be understood from the expansion of this generating function g of xt. Then question number 6, if the parity of operations do not change, then the if the parity operations do not change the function, actually sign of the function, then the function is said to have even parity, positive parity, or the function is said to be parity of the function is said to be plus 1. So either you can go for even, positive, or plus 1 parity. All these are the same. So all these functions which are supposed to have this type of parity, all these are called as even parity function, and therefore this is the true statement. So we are asked whether this statement is true or false. If the parity operations do not change, that is what the sign of the function is said to have even parity. So this is the true statement. Then question number 7, if the parity operations change the sign of the function, that means when this operator is operated on this particular function f of x, if its sign changes, becomes f of minus x, so such type of operator or such type of function is said to have odd parity. So read the statements once again. If the parity operations change the sign of the function, then the function is said to have even parity, or parity of the function is plus 1. That is a wrong statement or the false statement, and the correct statement is that if the parity operation changes the sign of the function, then the function is said to have odd parity, or the parity of the function is said to be minus 1. So even parity, odd parity, and plus 1 parity, minus 1 parity, these are the different types of terms that are used in mathematics to understand this. Then question number 8, hn of 0 is equal to 0 and hn of 0 is equal to minus 1 raised to n by 2 into n factorial upon n by 2 factorial are the properties of Harmonic function. We have to identify what happens to that, means what happens to value of n when n is even or odd, when we get hn of 0 is equal to 0, as well as when we equip n is equal to or even, that hn of 0 is equal to found to be minus 1 raised to n by 2 into n factorial upon n by 2 factorial. So here also we have to go for its expansion, this generating function g of xt for this particular function is e raised to plus twice xt minus t square. So here we have to put this particular function in this case. That is what we have to go for this put this x is equal to 0 as we have been given here. Therefore this g of 0 2 is equal to simply this is e raised to minus t square. So go for this exponential expansion of this term, e raised to minus x square minus t square, and this expansion also gives you I think you might be remembering, this expansion gives you 1 minus, then it is t square plus t raised to 4th upon 4 factorial minus t raised to 6 upon 6 factorial, and so on. So all such odd and even terms, odd terms are not there, only even terms are there. And nth term in this series, if it is obtained, it is to be minus 1 raised to n into t raised to 2n upon, this is n factorial, and plus some higher order terms are also there. So rearranging these terms, we get this particular nth term can be written as minus 1 raised to n divided by, this is n factorial, into, this is I can write this as 2 raised to n factorial into t raised to n upon 2n factorial. So here this expansion, while one goes for this expansion of this Hermite generating function of Hermite polynomial, I have to write this particular coefficient in terms of this. So this is the actual coefficient which we have obtained here. So in this case, when n is equal to 0, then I get this for odd n, all odd n, since there are no t raised to 1, t raised to 3, t raised to 5 terms appear. So all this hn of 0, when this n is odd, they do not appear. That means hn of 0 is equal to 0 when this n is equal to odd. So this is one term here, and this hn of 0 is equal to minus 1 raised to n by 2 upon n by 2 factorial. This 2n is n is replaced by n by 2, so I'll get it to be n factorial, and therefore this will appear when this n is replaced by n by 2, or it is twice n, so that is going to be even. So when this will be possible when n is odd, and this is possible when n is even, and therefore option A and option B are not correct option, but the option D is here. When n is odd, we get this hn of 0 is equal to 0, and when n is even, we get that term minus 1 raised to n by 2 into n factorial divided by n by 2 factorial. So that is possible case in this case, and therefore D is the correct option of this question number 8. Now question number 9. This is again a simple property of one of the function or polynomial we have seen. H dash n of x is equal to twice n hn minus 1 of x. How to get this property in case of Hermite polynomial? That is what we have to differentiate this generating function with respect to x. We get this particular property. So both of these properties mentioned here, hn of x is equal to minus 1 raised to n multiplied by hn of minus x. So this is a parity property, and this is a simple differentiation of the generating function of Hermite polynomials, and therefore both of these properties are the properties of this Hermite polynomial. So whenever we are asked, now this is very simple question in fact, so we use these symbols hn of x to define the Hermite polynomial. So naturally all these properties are properties of the Hermite polynomial. Question number 10 is also just same. So let's remember, in our usual almost all textbooks we use jn of x, that is the symbol or the used for this Basal function of first kind, and therefore these both of these properties given, jn of x is equal to minus 1 raised to n jn of minus x, this is the parity property of this Basal function, and jn minus 1 of x minus jn plus 1 of x is equal to twice jn dash j dash n of x. These are the properties of the Basal function of the first kind. So just identifying the symbols, we can identify for which type of function these properties are there. Okay, now there is one more important aspect which we have already discussed, but here all these functions, special functions, these can be defined from certain function, and all these are certain formulas, and these formulas are called as a Rodrigues formula. So Rodrigues formula for this Hermite polynomial is given as, there are 4 options given. So this formula, if you remember, it is given by hn of x is equal to, so see how the symbols have been changed there. hn of x is equal to minus 1 raised to n multiplied by e raised to x square into d raised to n upon dx raised to n multiplied by e raised to x square minus x square. Okay, e raised to minus x square. And see here in our given options, h n of x equal to minus 1 raised to n e raised to x square into d raised to n upon d raised to x dx raised to n into e raised to minus x square. So this is the correct as per our theory, and therefore this is the correct option. In other options, this n x the middle term e raised to x square has been replaced by e raised to minus x square. That is wrong. As well as e raised to minus x square in this bracket has been replaced by e raised to x square. So this is also not correct. Here minus 1 raised to n into e raised to x square is there, but this d raised to n upon dx raised to n in the bracket, sign of this e raised to x square minus x square has been changed. So this is also not correct. So just by making a small change, either plus or minus, or writing something in the numerator, something in the denominator, etc., we can see here this in the option 4, this n has been changed by n minus 1 in both this differential operator in the numerator as well as denominator. So this is also not a Rodrigues formula for this Harmonic polynomial. So this is a memory question, as I said. So h n of x is equal to minus 1 raised to n into e raised to x square d raised to n upon dx raised to n into e raised to minus x square. Therefore option A is the correct option for the Rodrigues formula. Now question number 12. This is what we have to go for, a generating function of the Legendre polynomial. So already we have seen generating function of Legendre polynomial is 1 minus twice xt plus t square, and this is to be raised to minus 1/2. We have to expand this g of xt, and we get a polynomial in t raised to n multiplied by Pn of x, and that's what this generating function, when it is expanded around t is equal to 0, we get this particular equation here, and therefore n is equal to 0 to infinity, and that's why we call this, out of this given options A, B, C and D, naturally B is applicable for Harmonic, so this C is applicable for Basal, and it is very easy to identify. This is the correct option. A, g of xt is equal to summation from n equal to 0 to infinity Pn of x into t raised to n. So this expansion of this generating function, that gives you a power series in t raised to n with certain coefficient, and all these coefficients are nothing but your Legendre polynomials of order n equal to 0, 1, 2, 3, 4, etc. So all Legendre polynomials can be obtained from this. That's what question number 12, correct answer is B. Now question number 13, similar question. Generating function for Harmonic polynomial is also given by, okay, so here also when we expand this generating function for Harmonic polynomial, we get this generating function for the Harmonic polynomial. You have already seen this. This is given by e raised to twice xt minus t square. When we expand this, we get a summation over n equal to 0 to infinity. Then we get a power series in t raised to n upon n factorial. Okay, this power series t raised to n upon n factorial, and if it is at the same time it is multiplied by some constants, these are called as h n x of r. These are the polynomials, Harmonic polynomials, and therefore correct option of this is B. So this A is applicable for Legendre, C is applicable for Basal, but here in this case this n varies from minus infinity to plus infinity, whereas in both of these cases n varies from 0 to infinity. So these are the positive and negative values of n are to be taken here. Here only positive values of n are taken in both the options A and B. So the correct option for question number 13 is B. Now similar question again, generating function of the Basal function of the first kind as is given by, already we have seen this is for Legendre, this is for Harmonic, so naturally this is for Basal function of the first kind. Therefore question number 14, C is the correct option. And the last question in this particular case, this is a question number 15. Rodrigues formula for Legendre polynomial is given as. So this is again a very simple theoretical question, wherein the correct Rodrigues formula for Legendre polynomial or function is given by 1 upon 2 raised to n into n factorial multiplied by d raised to n upon dx raised to n into the bracket x square minus 1 raised to n. So out of this, the correct option for this question number 15 is okay, this is option D. Now here 2 raised to n, n factorial d raised to n upon dx raised to n into x square minus 1. So this is the wrong, here n minus 1 is written there, that's why it is not correct. Option B here, it is 2 raised to n minus 1, that is the change. That's why this is not correct. Option C, the 2 raised to n into n minus 1 factorial, so this term is not needed there, so that is also not correct, and therefore correct option for this question number 15 is D as given here. So from this, actually these are the questions I have taken from a book by Idol publication. So these are the questions I have taken from this book from the Idol publication, and that particular thing shows you for this coming examination on this particular chapter number 4, where we have to get prepared, or how we have to get prepared. So make a table like this. So but complete table. First it is a function, then go for, so like this is a table here. Make a special table here. This is first, it is Legendre, then Harmonic, and then Basal. So these are Basal. Then first get the differential equation. So what is the differential equation for a given function? Write differential equation for this, for this, for this. Then go for the actual polynomials or the functions, or you can go for the solutions too. Solutions for legendary differential equation, solution for Harmonic, solution for Basal, that can be written. Then we have seen how to use this generating function. What are the different generating functions? G of xt for this, for this, for this. So by comparing this, we can very easily understand what are the generating functions for different types of different polynomials. Also we can go for Rodrigues formula for this. So Rodrigues formula. So write the Rodrigues formula for Legendre, for Harmonic, for Basal. Then go for some of the properties like parity. So write expressions, parity expression for Harmonic, for Legendre, for Basal, and there is 3 terms recurrence relation. Okay? 3 terms recurrence relation. So once we write the 3 terms recurrence relations for all these 3 types of functions, I am sure in the coming examination, whatever MCQ that will be asked over the chapter 4 will be totally based upon this very simple table. So while you are studying, make such a exclusive table containing each function and all its parameters, like differential equation, its solution, its generating function, Rodrigues formula, its parity, and other 3 terms recurrence relation, and in a tabular form. Then it is very easy for you to answer the questions related to this module number 4. I hope this would help you again for the coming examination. So in this TYBSc MMP paper 1, that is only one part of this module number 3 is remaining, chapter number 3 is remaining. Some of the questions that also will discuss in the next video. So thank you for patience listening.